It's a pleasure always to be in Paris. I'm going to talk about new approaches to cancer therapy, and what I will tell you is truly rather unusual, I think. And I'll see whether I can convince you that what I'm going to say is worth trying in the clinic. The work that I'm going to discuss was done in collaboration with a microscopically small biotech company in the US called LixT Biotechnology, and I'll tell you which drug they have that I think is interesting to work with in oncology. So if I summarize 20 years of targeted therapy in a few slides, then it is that if you have a signaling pathway that is activated by mutation, that initially leads to good success if you inhibit that pathway with a small molecule inhibitor. But sooner or later, mostly sooner, you see that secondary mutations arise that reactivate the pathway, leading to resistance, right? We call this on-target drug resistance. But cancer cells have many tricks up their sleeve to evade targeted therapies. The alternative would be to mutate downstream and make sure that the signal comes through in spite of the fact that there is a blockade upstream in the cascade. We call this downstream inhibition. And then there is the tricky parallel pathway inhibition where other receptors get activated that signal through the same pathway. So one way or the other, the cancer cell manages to get the signal back because the cancer cell is addicted to the signal that comes from the mutated oncogene and will one way or the other get that signal back. So as long as we are inhibiting oncogenic signaling in cancer cells, we are essentially fighting a losing battle in advanced cancers, I should say, because in advanced cancers there's simply too much heterogeneity to get long-lasting tumor control. So what I'm going to tell you is that we have been doing it the wrong way around for the last 20 years, and that instead of inhibition of oncogenic signaling, we should do the opposite. And let me tell you why I think that. So oncogenic signaling gives us these hallmarks of cancer that are distinct for cancer cells, like limitless proliferation, insensitivity to anti-proliferative signals. They no longer need growth factors. They can evade apoptosis, you name it. But we always focus on this aspect of the hallmarks of cancer, but there is the other side of the hallmarks of cancer, which are the stress responses that are inherently linked to the activation of oncogenic signaling. All cancer cells experience, to some degree, DNA damage stress, oxidative stress, mitotic stress, metabolic stress, and therefore cancer cells need to balance, on the one hand, the acquisition of the cancer phenotypes with managing those stress responses that are the flip side of that. And that means something that is, I think, at the heart of what I'm going to try to tell you, is that tumorigenesis makes that the cancer cells get the optimal level of mitogenic signaling and not the maximal level, because the maximal level would increase these stress responses to the degree that the cancer cells will not proliferate. So it's a trade-off for the cancer cell. More signaling is good, but it gives more stress. And where the optimum may differ from every cell, but sure enough, you can assure that the cancer cells have found that optimum so that they proliferate optimally. So, as I said, we try to inhibit the oncogenic signaling to get rid of the hallmarks of cancer, but how about the opposite? Where we hyperstimulate oncogenic signaling deliberately, on the one hand, that should increase these hallmarks of cancer that are good for the cancer cells, but it will also increase their stress responses. And you could imagine a scenario where you, on the one hand, activate oncogenic signaling and then combine that with drugs that inhibit these stress responses that cancer cells need to survive the hyperactivated oncogenic signaling. And this combination of, on the one hand, increasing oncogenic signaling, and on the other hand, inhibition of the stress responses, we call a paradoxical intervention, because it is counterintuitive to activate oncogenic signaling in a cancer cell that already has that. Right? So how are we going to do that? We need to answer two questions. One is, how do we hyperactivate oncogenic signaling in a cancer cell where oncogenic signaling is already active? And then second, which of these stress responses do we need to perturb to get maximum therapeutic efficacy of this hyperactivation of oncogenic signaling? So I have answers to both questions for you, otherwise I probably wouldn't talk about this topic. But I just want to make sure that you understand that there is a lot of evidence in the scientific literature to support this notion that more oncogenic signaling is not better. And one piece of very elegant evidence comes from the lab of Harold Farmas, who on the one hand noticed that mutations in the EGFR are mutually exclusive with oncogenic mutations in KRAS, and then he tested this experimentally by making a double transgenic mouse that expresses in the same lung epithelial cells both KRAS and EGFR, and those animals did not develop lung cancer, or when they did develop lung cancer, they only expressed one of the two oncogenes and never both. So that says that more oncogenic signaling is not good, and in fact prevents cancer rather than that it stimulates cancer formation. So what I'm going to focus on is protein phosphatase type 2A, or for short PP2A, because PP2A activates Wnt beta-catenin signaling, I should say it inhibits beta-catenin, and therefore the activation of PP2A would inhibit beta-catenin signaling. It also, when it's active, it inhibits MEK-ERK signaling, and it inhibits PI3 kinase AKT signaling. So in fact, three major cancer pathways that are relevant to cancer development, PI3 kinase AKT, MAP kinase, and Wnt pathway are inhibited when PP2A is activated. So one would think that if you now do the opposite, namely to inhibit PP2A, you would activate these three pathways, and you would get this hyperactivation of signaling. And there is one, as I said, microscopically small company in the US that has developed a PP2A small molecule inhibitor called LB100. And LB100 inhibits the catalytic subunit of PP2A. And I'll come back to the chemo and radiosensitizing potential of this drug, because this is a session on chemotherapy. This molecule has been shown to be pretty potent in sensitizing to chemotherapy. And remarkably, you would think that PP2A is a molecule that you shouldn't touch in oncology because it is too pleiotropic and therefore very toxic. There's one drug that many of you may know called okadaic acid, which is extremely toxic. And the remarkable thing was that when LB100, which has no structural resemblance to okadaic acid, was tested in the clinic, it was very well tolerated and never went above grade 2 toxicity. So we can selectively inhibit PP2A with a relatively non-toxic small molecule called LB100. So what happens if we take colorectal cancer cells, because I told you that MAP kinase and Wnt signaling, these are typically pathways that are activated in colorectal cancer. If we treat with increasing concentrations of LB100, you see that in fact the cells become growth inhibited. And if you then look at what happens, you see that indeed in colorectal cancer cells like SW480, where a KRAS oncogene is already driving the MAP kinase pathway, you see that phosphor-ERK is increased, phospho-Jun is increased, we see that active beta-catenin is increased, and that means that in these cells we further increase mitogenic signaling, and that is anti-proliferative because at the same time we see DNA damage go up, we see phospho-CHK1, unfolded protein response, we see also these stress response pathways being activated, and the same in a BRAF-mutant colorectal cancer setting. So yes, there is evidence for increase of mitogenic signaling, but it becomes prohibitive due to the activation of the stress responses, right? So this is not very impressive anti-proliferative capacity. So as I said, we don't think that this by itself is enough. You need to do something else. You need to perturb the stress responses to get effective killing. And to do that, the postdoc that worked on this project from Brazil, Mateus Henrique Dias, designed a small library of 164 compounds, and you see that here, that he tested, and these were drugs that target these stress responses: metabolic stress, proteotoxic stress, mitotic, oxidative, DNA damage stress, apoptotic molecules, and tested these compounds in 15 concentrations in the presence and absence of this drug LB100 to ask, is there any inhibition of these stress responses that is far more potent in the presence of LB100 compared to the absence, right? And he did that in 2 colorectal cancer cell lines, HE29 SW480, BRAF, and KRAS mutant. And you see here that the outliers on the negative side, that means if you're below 0, that means the drug is more effective in the presence of LB100 compared to the absence. We see that the WEE1 inhibitor, like adavosertib, and the CHEK1 inhibitors stand out as being particularly toxic in the presence of LB100. Now, this was, of course, a very limited survey because we look at 164 compounds. So Matthäus also did an unbiased CRISPR screen where he simply knocked out all the genes in the human genome, plus or minus LB100, and asked which gene is more toxic in the presence of LB100 compared to the absence. And the top outlier here is protein phosphatase type 1, PP1, because now you have no phosphatase activity left in your cell. But another prominent hit here is again WEE1. That was the target of the small molecules that also scored in this assay, like adavosertib. So you see that the CRISPR screen and the compound screen both point at WEE1 as a particular vulnerability of cells treated with LB100. And therefore, we did some initial validation of these drugs where we took this WEE1 inhibitor called adavosertib, a AstraZeneca drug, and LB100 in a panel of colorectal cancer cell lines of very different genetic backgrounds, either in long-term or here in short-term IncuCyte assays. And you see that in each case, you see a remarkable synergy between adavosertib and LB100 in the killing of these colorectal cancer cells. So it seems that there is very little context dependency because whether the cells are no mutations in the PI3 kinase pathway or have KRAS or BRAF or other mutations, we see that no matter what we do, we see synergy. And in fact, we can broaden this concept to other cancer models. This is for pancreatic cancer cell lines that typically are KRAS mutant. We see the synergy. Here we have cholangiocarcinomas, where only half of them have KRAS mutations, but also those that don't have KRAS mutations seem to suffer if we combine LB100 with adavosertib. So how does this work? Why do we get toxicity when we combine LB100 with a WEE1 inhibitor? We worked with Rene Medema's lab at our institute, Jonne and Anouk, to film cells as they asynchronously go through the cell cycle. So you can film cells, individual cells. Here we see about 50 cells, where each horizontal line is one cell, and we film them as they are in mitosis. And you can, of course, see when they are in mitosis, and a typical cell that is treated with control medium will spend about 45 minutes in mitosis and then go on into the next G1, right? So these are control cells, asynchronous. They each have their own point in time where they enter mitosis and they go into the next G1. If we treat with LB100, we see that the cells enter mitosis earlier, and many cells spend a lot of time in mitosis during the 24-hour filming and are unable to escape. If we treat with adavosertib, mitotic entry is even early because, of course, WEE1 is a kinase that prevents premature mitotic entry. So if you inhibit that kinase, mitotic entry is facilitated. But if you look at the combination, we see that many cells that enter mitosis, in fact, all of them, are unable to leave mitosis. They get stuck in mitosis. And if you then look at what happens to these cells, we see that normal cells have beautiful recognizable chromosomes during mitosis. But if you look at the cells treated with the combination, it can only be described as pulverized chromatin. You cannot recognize the chromosomes anymore. It's a complete mess, and that leads to massive apoptotic death in the cells treated with the combination. So what is happening in cells that are treated with this combination, that their chromatin becomes such a mess? The answer is that the cells, by being hyperstimulated in their cell cycle, are experiencing massive DNA replication stress. And you can tell that there is a marker of mitotic cells called phosphohistone H3 that should only be active in mitosis, and only cells with a 4N DNA content should have phosphohistone H3, which you see for the control treated cells is true. Here's the marker phosphohistone H3 for cells that have 4N DNA content. If we treat with the combination, we see that nearly all cells that stain positive for phosphohistone 3 are having between 2N and 4N DNA content. That means they are actively replicating DNA, but they already stain positive for a mitotic marker. So they were pushed into mitosis without having completed DNA replication. And that is, of course, a lethal event because you cannot segregate your chromosomes if you don't have a 4N DNA content, right? And I would like to point out that this, in fact, is also most likely the reason that a WEE1 inhibitor is effective in combination with chemotherapy, because the only scenario in which WEE1 inhibitors so far have proven to have some effect is in combination with chemotherapy. And Nick Turner very elegantly showed that, that chemotherapy induces DNA replication stress, obviously, and then you push the cells into mitosis by inhibiting WEE1 with that replication stress, and that leads to cell death. And there have been positive trials with adavosertib as a WEE1 inhibitor and chemotherapy in patients with platinum-resistant ovarian cancer. It is unfortunate that AstraZeneca decided to discontinue adavosertib development, but there is a second-generation WEE1 inhibitor from a company called Zentalis that has a molecule called ZNC3 that is progressing through clinical development. And I think that that will be a successful drug in combination with chemotherapy for the reasons that I just mentioned. Now, how does our combination of an LB100 plus WEE1 inhibition compare to, for instance, adavosertib with doxorubicin or gemcitabine? Here you see a number of cancer cell lines, colorectals, pancreatic, or here cholangiocarcinomas, and what we show here is the synergy score. A 0 synergy score means there is no synergy, and if it's above 10, the synergy is significant. That means that the drugs really enhance each other's activity. So if you look at adavosertib plus doxorubicin, adavosertib plus gemcitabine, the red and the green, you see that in all cases there is enhanced activity, but it doesn't quite reach the threshold of 10 where we are really speaking of synergy. And if you now look at our combination of adavosertib with LB100, you see that in all these cell lines we reach the threshold of above synergy. So yes, there is synergy between adavosertib and chemotherapy, but the combination of adavosertib with LB100 seems to be a more potent combination than the chemotherapy combination. So can this be done in vivo? Is this not too toxic? I told you that LB100 in patients seem to be very acceptable. It is also the case in our mouse experimental models. We worked with Alberto Villanueva in Barcelona to take orthotopic PDX models of colorectal cancer, 3 different ones. And you see here that if we treat with either the vehicle, the monotherapies, or the combinations, you see that the combinations are by far the most effective. And what is also interesting is that whatever is left here in terms of volume is mostly inflamed stroma and necrotic cells. Only these little rims here are viable cancer cells. There's hardly any viable cancer cells left. And the volume that you see is an overestimation of what there is left in terms of tumor mass. This is all seen in the absence of any overt toxicity as judged by weight loss. We see the same in cholangiocarcinoma models. This is more conventional xenograft subcutaneous. Again, the combination being superior in the absence of weight loss. So I told you at the beginning of my talk that the biggest problem we have in oncology is resistance. So we figured that any drug combination can lead to resistance, no matter how powerful. So in all likelihood, this combination of LB100 with adavosertib would also lead to resistance. So we started to ask the question, how does a cancer cell evade this stress that is imposed by hyperactivation of mitogenic signaling through LB100? So Matthias did a very simple experiment. Again, we are a CRISPR screening lab, we can do that. So we took colorectal cancer cells, treated with LB100, and this is a CRISPR-A screen. CRISPR-A overexpresses genes. So it asks the question, which genes, when overexpressed, make the cells more vulnerable to LB100? The top outlier is c-MYC, and then you see here a number of hits in the MAP kinase pathway and in the Wnt beta-catenin pathway. So if you hyperactivate Wnt beta-catenin and MAP kinase signaling, the cells become more vulnerable to LB100. Why is that? Because that is the pathways that this drug already hyperactivates. And if you now force more expression of these genes in this pathway, you get more toxicity by more hyperactivation. The converse is also true. If you do a CRISPR knockout screen and ask which genes confer the most resistance to LB100, you again see Wnt beta-catenin signaling stand out and MAP kinase signaling. And if you put all of those genes of the two screens in a string diagram, you have one node around MYC and one node around beta-catenin that seems to be central in modulating the response. More MYC is bad, more Wnt signaling is bad. And conversely is also true. Less MYC is good for cells treated with LB100, and less Wnt beta-catenin is also good, right? So there is, of course, a case of NMYC amplified neuroblastomas, and I thought of work that I did as a postdoc with Bob Weinberg back in 1986, where I showed, here you have it, 1986, NMYC amplification causes downregulation of class 1 HLA antigens in neuroblastoma. This was a case of immunotherapy escape avant la lettre, as you say here in Paris. Nobody really cared about it because nobody thought at the time that the immune system did anything to cancer cells, so why bother to pay attention to this? But I had these cells in the freezer, and I had made a panel of isogenic cell lines that expressed increasing concentrations of NMYC. The purpose of this, of course, was to show that the HLA antigens went down as MYC went up, but these cells were sitting for 40 years in the freezer in Amsterdam, and lo and behold, they grew again, and we could test whether LB100 is now more effective in the NMYC amplified derivatives compared to the parental cells. And sure enough, we saw a rather sizable shift in IC50s and also a rather sizable shift in long-term colony formation assays. So it is true across the board that more MYC makes you more vulnerable to this drug called LB100, right? So now what happens, and this I think is by far the most exciting part of the work that I'm going to tell you, is how do cells develop spontaneous resistance to the combination of LB100 and adavosertib. Here you see that this combination is pretty effective in SW480 colorectal cancer cells, but if we treat them for 4 to 5 months with this drug concentration, lo and behold, you get cells that become resistant. No surprise. But the question is, how do they manage to do that? The problem is hyperactivation of oncogenic signaling. This is what they need to escape. The first thing that is striking, if you look at these cells, is that the parental cells have a rather messy karyotype, being aneuploid, and the cells that have become resistant have reduced their complexity of the karyotype to near diploid status. So you see a marked collapse of aneuploidy to a near diploid phenotype, which is, of course, a marker of less malignant behavior, because cancer cells typically have aneuploidy as a marker of aggressiveness. So what is the consequence of the fact that they have gone from, on average, some 75 chromosomes to some 50 chromosomes? We did single-cell RNA sequencing of these cells and found that the SW480 resistant cells are very distinct in transcriptome from the parental cells here in red. The blue ones are the resistant single cells. These are UMAP plots where you see the different behavior of these cells. Now, if you now ask which pathways are different in these cells that have developed resistance, you see that Wnt beta-catenin signaling is down, MYC targets are down, and E2F targets are down. 3 of the 4. Incidentally, MAP kinase is not changed, but MYC, E2F, and Wnt beta-catenin is significantly reduced. And that would suggest that these cells had to give up a significant degree of oncogenic signaling to be able to tolerate a drug that activates mitogenic signaling. So how have they done this? They have done this, and you see that also here by a Western blot. We see that the parental cells have high levels of phospho-Jun that is gone in the resistant cells. We see that the BCL9L is reduced, which is a downstream target of Wnt signaling. MYC levels are down, but importantly also the stress levels are down. DNA damage is down in resistant cells. Phospho-Chk1, phosphohistone H3 is down. So you see that they have managed to downregulate oncogenic signaling as a resistance, and that is giving them the benefit of having less stress responses in these cells, right? So, what is the consequence of this downregulation of oncogenic signaling? If we grow the cells in 2D, they are still able to grow because, of course, we selected for cells that grew in the presence of drug in 2D. But if we now plate them in three-dimensional culture anchorage independent growth, which is the sort of Poorman surrogate for oncogenicity, we saw a dramatic drop in anchorage independent growth of the resistant cells. And more importantly, when we injected these resistant cells, combination resistant cells, in animals, they no longer form tumors, whereas the parental cells form tumors. So the take-home message is that cancer cells in which you hyperactivate oncogenic signaling are forced to evolve to a less malignant phenotype. They do so by throwing out chromosomes that results in downregulation of oncogenic signaling. There's enough oncogenic signaling so that these cells are able to proliferate in 2D, but they have lost their ability to grow in 3D and have lost their ability to grow in vivo. So this approach we call a paradoxical intervention. And you knows my wife Sophie, who is in psychotherapy, and she told me that in psychotherapy, paradoxical interventions are characterized by a deliberate reinforcement of the pathological behavior to improve the clinical condition. Such a counterintuitive approach can be considered when more conventional therapies fail. This comes straight from her textbook on psychotherapy. So have we now met the criteria of a paradoxical intervention? We do a deliberate reinforcement of the pathological behavior by deliberately hyperactivation of oncogenic signaling, right? And we have improved the clinical condition, for sure, for the mice because they no longer form tumors when they are now resistant. So we can force the cells to become better behaved by activating oncogenic signaling further. And I would also argue that this counterintuitive approach should not be a first-line therapy, but hopefully we can test this soon when we have patients that have failed more conventional therapies. So my take-home message is simple. Hyperactivation of oncogenic signaling is a viable cancer treatment strategy as resistance select for cells with reduced oncogenic phenotype. And on that note, I'll stop. All of this work was done essentially by a single postdoc from Brazil, Mateus Henrique Dias, with help from postdocs from Rene Medema's lab and Alberto Villanueva, who did the animal experiments with us. And here are the people that fund our research. I'll be happy to take any questions.